we are going to be doing the calculus with parametric curves. In fact, we are going to find out how to integrate, well, not so much integrate, we'll do one of those, but how we're going to find derivatives of parametric curves and how we can use those derivatives to answer very basic questions that you would have done back in Calc 1. So I want you to imagine that I have a parametric curve, and so we'll make it a very general parametric curve. And you went into that Desmos thing, and when you put it into Desmos, it ended up looking like this. They don't need to be loops, but let's say this is the curve and that's the orientation, right? Now, you know, you can just plug it into Desmos and it does it, and you got your guy. So let's suppose I have this point here, and it happens to be when t equals 3, right? Would you agree that there's a tangent line at t equals 3 to that curve? That seems reasonable. Tangent line. Now, if you have a tangent line, you have a slope of a tangent line, right? You have a number that line is, right? It's got a slope. So doesn't that mean that there should be a derivative to this curve at that point? And so the answer is yes, there is. So how do we get that derivative? Well, it's a remarkably simple formula. We're going to call it dy by dx, right? We're going to use that notation. Remember the f dashed x notation, dy by dx notation. You might even have seen the y dashed notation, but this is the notation that we're going to use. The derivative at that point is given by this formula. Well, is it not remarkably neat? All you do is differentiate this guy with respect to t divided by this guy with respect to t. So let's do an example then. That's the only formula you need to find the first derivative of a parametric curve. So let's suppose x was t squared plus t, and let's suppose y was e to the 2t plus 1. And I would like to know what the derivative is. Then I would do dy by dt divided by dx by dt. So you typically are going to get a fraction. And if you differentiate this guy, you get e to the 2t times 2. And if you differentiate this guy, you get 2t plus 1. So far, so good. Can we pretend, I know it's not, can we pretend that guy is him, right? Just for argument's sake. If I wanted to find the slope of that tangent line at t equals 3, it would look something like this. Oh. Derivative, vertical line. You put a little t equals 3. That's just the notation that we use. What that says is I'm going to find the derivative at t equals 3, and that vertical line is part of the way you write it down. So it's going to be 2 lots of e to the 2 times 3 over 2 times 3 plus 1. So that's 2e to the 6 over 7. So now I know the slope of that red line. It's whatever 2e to the power of 6 divided by 7 is. I'm amazed, still amazed, by how kind of tidy that logic is. Because these weird things, can't they be spirals and, oh God, all sorts of weird shapes, right? Parametric curves can be weird shapes. But if you want to find the slope of the tangent line at any given point, don't you basically just do the derivative of the y value with respect to t and divide it by this guy? Have you noticed that when you do parametric curves, your answer is also going to be in terms of the parametric curve? The answer isn't xy over xy squared or anything, right? It doesn't have x's and y's in it. It just has the t in it. which is kind of nice because then when you want to do a point, don't you just plug in whatever t you're interested in? Now, imagine I wanted to find, and let's do a different curve, yeah. Try to think of a curve. Yeah, how about x equals 2 sine t plus 1 and y equals 2 cosine t minus 1. I'm going to go into Desmos with this guy. Yep, it's set up, just making sure it was. And we'll sketch them, and then we're going to do some calculus on them. We're going to find derivative, and we're going to see what that can do. So over here, I'm going to have 2 sine t plus 1. So there's the t. There's a 2 sine t. There's a plus 1. And 2 cosine t is going to be the next fella. I'm going to take away 1. And I'm going to do this fella here. Hopefully pi will work. Yes, it did. Right. Not the most impressive looking curve in the world, isn't it? Basically just a circle off-centered. But it does exactly what I want it to do. Let's move it a little bit, maybe make it a little bit bigger. Wouldn't it be nice if I could find its derivative at any point, like when t equals 2 or something, right? Be nice if I could do that. And we're going to do that as one of our questions. So I'm going to put these questions in. Find the derivative when t equals, well, 2 is a bad choice. Let's say pi upon 4, because it's trig functions. We get nicer numbers with that. So I would like to know what that looks like. Now, on this particular shape, there's some very interesting derivatives we might want to know. I know you can read off the answer here, but wouldn't you like to know when the curve had a horizontal tangent line? Because doesn't that mean you're at the top of a hill or the bottom of the valley? So I would like to know when the derivatives are horizontal, right? When we have zeros. So that's me writing down my next question is, we're going to find when the derivative is equal to 0, right? Horizontal. And wouldn't it also be interesting to know when the curve has a vertical tangent line? And so I'm going to put that down as C. We're going to find when the derivative is infinite. So let's return now and see if all of those things are possible. And the good news is that they are. So here is my parametric curve. Question A was find the derivative. So that's dy by dt divided by dx by dt. And if you differentiate this guy, you get 2 sine t. Do you get anything else if you differentiate 2 cosine t? Is that it, or have I missed something?
You have to have a negative.
Correct. And if you go the other way, you get 2 cosine t. Everybody happy with that one? Now, I could simplify that, but I'm not going to, because it actually makes B and C a little bit harder to do. So I want to find the derivative at pi upon 4. So dy by dx at t equals pi upon 4 becomes negative 2 times the sine of pi upon 4 over 2 times the cosine of pi upon 4. And that guy is root 2 over 2. And this guy is root 2 over 2. God, there's a lot going on here. Actually, doesn't the answer just come out to be -1? So if you can imagine our circles kind of over here somewhere, it looks to me like it's probably going to be somewhere over there, right? Whoops, wrong place. Probably going to be somewhere up here, right? Now, how about finding when this circle is horizontal? There and there. By that, I'm asking us to find out the t where that happens. So we're going to find when a given derivative is equal to 0, which means that we're going to be solving -2 sine t over 2 cosine t equals 0. One of the advantages of leaving these questions as a fraction is for questions B and C. If you want to know when a fraction is 0, don't you only need to worry about when the top is 0? Agreed? And this guy is at t equals 0, at t equals pi, at t equals 2 pi, at t equals 3 pi for eternity, right? Agreed? Now, since we restricted ourselves only to that range, doesn't that mean that's our solutions? Would it be reasonable to assume that that guy is actually the same place as that guy? So when you look at our picture, do you see there's only 2 locations? It could be that this guy here is at 0 and at 2 pi, and this guy here is what you get when t equals pi, right? You could find out where on each of the circles, couldn't you? By just plugging 0, pi, and 2 pi in. So let's see if I can do that. If I do 0, it's going to be 2 sine 0 plus 1, which is 0 plus 1, which is 1. And the y coordinate is going to be 2 cosine zeros, take away 1. That's going to be 2 take away 1 is 1. So we are looking at the position 1, 1, which I bet you is that guy there. So not only do we know where the tangent line is horizontal, can't we also find the coordinates of where that happened? Right, because once you know what t is. If you do pi, can you trust me you're going to get that one down there? And if I do that, then t equals pi, the x coordinate is going to be 2 sine pi plus 1, and the y coordinate is going to be 2 cosine pi, take away 1. And what's that? That's nothing, add 1 is 1, -2, -3, there you go. And I bet you that guy there, I'm here, is 1, -3, right? Everything matches. So if you want to find out when a derivative of a parametric curve is 0, don't you only need to find out when the top piece of this fraction is 0? The last question is find out when it's infinite. So we are going to go for when is this guy vertical, right? Infinite, or more precisely, undefined. Well, we have -2 sine t over 2 cosine t. And when is that infinite, undefined? When will that fraction be undefined? Infinite, if you like.
When cosine of t is 0?
Okay, when the bottom is 0, which is, as you said, when the cosine is 0.
Well, we also got to make sure the top isn't 0 because it could be defined if the bottom and the top are both 0, but cosine and sine will not be 0 at the same time.
Correct. So we don't need to worry about that. And typically you don't need to worry about the top and bottom both being 0, because what you should do in another situation is should always factor and cancel so your fraction is in its simplest format. And when your fraction is in your simplest format, you're never going to have 0 over 0. So theoretically that can happen, but as long as you do the math, you'll avoid it happening, right? You'll make sure it won't happen. So we're looking for when is this going to happen? Would you agree it's pi over 2, 3 upon 2 pi, and they're the only ones that work because we are sticking to the range 0 to 2 pi. And I don't know which one is. I'll have a guess. Can you imagine that when t equals pi upon 2, you end up with that one, and then when you do 3/2 pi, you end up with that one, right? Couldn't we just plug in t equals pi upon 2 to the parametric equation and get its coordinates? And couldn't we then do 3/2 and get its coordinates? And we would be able to tell for sure which one is which. Cool. So I can find derivatives of any parametric curve without too much work. And I can also tell you when it is 0, horizontal, and when it is vertical. So let's try another one. We'll start with find its derivative. And that's going to be 3t squared take away 3. And the top's going to be 4t take away 4. Agreed? So far, so good. Now, style points, very important. I'll pull out a common factor of 3 and a common factor of 4. Is there anything I can do on the top? Anything I can factor, for instance?
T squared minus 1. Go ahead.
Right.
I was gonna say,
Anybody?
since it's the difference of squares, you can do t plus 1, t minus 1.
Now, can you see cancelling?
Minus 1.
And that is part of what you must make sure. Remember, Tim was saying, wait a minute, you could get 0 on the top and 0 on the bottom, and you should always check in case that happens. If you factor things and cancel, won't you eliminate the 0, 0 issue? Because if there's a 0 on the top and the 0 on the bottom, can you trust me? There must be some cancelling going on, right? There's a common factor on the top and the bottom that's causing that typically. So we are looking at this fraction. I can tell you right now that won't this particular curve be 0 when t equals -1? Would you agree just looking at that fraction? Can you also look at that curve and say it will never be vertical? You'll never get the curve doing that, right? Why can I say for certain that this parametric curve won't do that thing? Can this ever be infinity? No, isn't there just a 4 on the bottom? It's going to be some number. So far, so good. Now, at t equals -1, the x coordinate is 2 lots of -1 squared, take away 4 lots of -1. And that's 2 add 4, so that's 6. And the y coordinate is going to be -1 cubed, take away 3 lots of -1. So that's going to be -1 add 3, I believe that's 2. So I can tell you that there's a horizontal, like a hill or a valley, right? And it's going to be happening at the point 6, 2. Agreed? Now, when we took out this common factor of t minus 1 cancelling with t minus 1, right? This guy here. We should do it to make it easier. But t minus 1 is 0 when t equals 1. So I'm going to call that a special point. because all sorts of weird things might happen at that point. Let's find the coordinates of it so I know where to look. Its x coordinate is going to be 2 lots of 1 squared, take away 4 lots of 1, which is -2. And its y coordinate is going to be 1 cubed, take away 3 lots of 1, which I believe is -2. So on this guy here, I am making a prediction that there's a hill or a valley, right? One of those guys. And it's going to happen at the point 6, 2. And there's going to be a special point. And that special point, I don't know what it is. It might not even be anything that special, but sometimes it can be. Right. So we are now going to go and see if what we've discovered matches the curve. Right. So let's look at this parametric curve and see if we can get the same features. So are you looking at the parametric curve right now? Okay, so I'm going to change this guy to 2t squared minus 4t. So I'll do that guy first. So 2t squared, take away 4t. And then I'm going to go to t cubed minus 3t. T cubed minus 3t. And we know that at the point 6, 2, at the point 6, 2, we should get, where is 6, 2? Did I screw that up? -1? What the heck's happened? Oh, well, at least one of our points has worked. Would you agree that -2, -2, the special point is a weird part of that curve? What I'm not finding is my zero derivative.
Would we not be able to find the derivative at the point -2 because the slope's going to be undefined at that point?
Well, this slope here is undefined, but that's my special point. I got that one. That worked really well, right? But we also found that there should be a zero tangent line at 6, 2. And I'm looking at 6, 2, and it isn't even on that curve, which means I've screwed up my calculations. So let me figure out what I should have done. At -1, that's 2. And at -1, that's 4. That's 6. Okay. At -1, that's -1. And that's 2. Okay, there's something weird happening here.
Do we have to take like the second derivative or something?
No. But that was a good point. I'm kind of happy that I found that one. I'm just amazed that I never found that one. The derivative is 0. And a 0 derivative is a horizontal line. There's no argument about that. Why is it not working? Come on, help me out here. It's normally I can't count. Okay, let me go back to the original question. Maybe when I see my working, I'll figure out why I didn't get the horizontal one, because I know I got the other guy. So the fact I got that guy kind of makes me feel good. Oh, I know. Darn it in space, I know. Does anybody else know what I did wrong?
Is it the derivative?
No, I didn't put -1 or my t range to include -1. There, can you see it now? Would you agree that's a horizontal tangent line? Right now, what do I need to make the other guy to be able to see him? Let's make it 3. There we go. Perfect. Can you see the special point at -2, 2 now? And can you see the horizontal tangent line? It was me not paying attention that the parametric curve has a range of t's that you're asking it to sketch, and I didn't have my range of t's with -1 as one of the choices. That's why I couldn't see it. Oh, I feel so much better. I was getting really worried about that guy. Isn't that amazing that with very simple algebra, we can find such interesting points on a parametric curve? Cool. Right, let's move onwards and do another question. Let's pick something from the homework. I won't do any of those guys, are too easy. Okay. All we're going to do in this question here, and this is a version of question 3, is just find its derivative. We're not going to find anything else. So this is just practice at finding derivatives. And the function is going to be a lot more messy because of that. So dy by dx, it's the derivative with respect to t and the derivative with respect to x. Right, you differentiate this guy, you get 8 plus cosine t. And if you differentiate this guy, won't you have to do a product rule? Since I don't want to write all the product rule down, you're just going to believe me. It's 6 e to the t plus 6t e to the t. Are we happy with that? Looking for style points. I don't see anything really great. That's fine. But if you're really, nah, that's it. I'm not going to even try and do it. I don't think you can do much except a minor. I'm not even sure it's worth doing, but I guess I could do that. Agreed? Now, the advantage of factoring, doesn't it make it easier if the question had been find out when the top's 0 or find out when the bottom's 0? Doesn't factoring just make it a little bit easier to solve? So that would be it, and always be on the lookout for oh, this is my answer. This guy is Weberstein's answer. I like my answer better. So I'm wondering why it did that. I don't know. Anybody want to throw in, why does Weberstein think that this is better than that?
Maybe it's not really rationalizing the denominator, but maybe they felt like getting that e to t out of the denominator was important.
Yeah, can't think of why it's important, but evidently they thought it was.
So they took it out and then they multiplied that 6 through.
Yeah,
It's
they
kinda
didn't
weird.
even take out 6 out of the bottom. You know, I mean, you'd think you could do that. That makes me wonder a little bit. I hope there are many flavors of the right answer, so that when you do these questions, what I would hate to happen is that you do this and it says wrong. And it's only wanting this. Because to be honest, I don't know how you would really know what it was looking for, because I don't see any logical reason why this is better than that. So let's hope that it's generous in the versions you can get. Okay, so I'm pretty comfortable that we can do questions where if I give you the function, you can get its derivative. Would you agree? Boom. So let's move on to find the equation of a tangent. That's a Calc 1 type question, right? Find the equation of a tangent line. Can we pretend that we have a curve and it looks like that? And I would be interested in finding, say at this point here, the equation of that red tangent line. And just for argument's sake, let's suppose it ends up being that, right? When we are finished, we are going to have an equation that looks like this. It won't have any t's in it. It will be y equals minus 3x plus 9, whatever it is. So they're going to give me the equation, and the curve is going to be the sine is 6t plus a cosine. And the y is going to be the cosine is 6t minus a sine t. And they want to find the equation of the tangent line at t equals pi. Right, so that's your question. Find the equation of the tangent line to this parametric curve at t equals pi. Okay. If you want to find the equation of a line, don't you need to know the point on the line? And don't you need to know the slope of that line? Okay, let's get the point, the coordinates of the point. How will I find the coordinates of, let's say it's that point there, using this and that? How will I find the coordinates?
You're gonna have to find out what point or what values for the the b, what values are gonna get you to that point on the curve on the xy. That makes sense.
Yeah. I was hoping people's just said, why don't you plug in pi here and here and get the answer? So the sine is 6 pi, which is nothing, plus the cosine of pi, which is -1, gives me the x coordinate is -1. The cosine of 6 pi is 1. The sine of pi is nothing. And there you go. We know the point. Just plug and chug. I don't need to solve any equation. Now, the second thing I need to know is the slope of the tangent line at t equals pi. How will I find the slope, right, it's a number, of the tangent line at t equals pi?
Don't you just find the derivative and plug it in?
Yep. So it's going to be dy by dt on the top, dx by dt on the bottom. And if you differentiate this guy, you get -6, the sine 6t, take away the cosine of t. And then you get 6 times the cosine of 6t minus the sine of t. And then you find the value of the derivative at t equals pi. And you get -6, the sine of 6 pi, so that's 0. Cosine of pi is -1, so take away -1. Cosine of 6 pi is 1, so that's 6 times 1. Take away a nothing, and I believe the answer is 1/6. So we know the coordinates of the point. We know the slope of the thing. Can you remember from math 94 how to get the equation of a line when you know the point and its slope?
So you can plug the values of the point in for x and y, and then you can plug the slope in for the slope in y equals mx plus b form.
Well, yeah. The version I'm going to do is called the point slope version, right? You remember that guy? And in this case, it's going to be y take away 1 equals 1/6 x take away -1. And the next couple of lines are just to make it look pretty. Yeah, I don't think it's going to be a really pretty question.
Are we allowed to leave it in point slope?
I wouldn't. I think it's pretty standard. The equation should be written as y equals. So that's good. That's good. Now, I don't know what WebAssign does, you know, what it would accept, but even if it does accept that, I think you should take it to there. Let me have a look. And WebAssign likes my answer, so that's fine. And so WebAssign is looking, at least in the answer I'm looking at, is looking at this one. So let's do a quick recap. If I give you a parametric curve, are you happy about finding its derivative dy by dx? You're comfortable with the process? Because you know how to do derivatives, right? So you can do dy by dt and be aware of cancelling, right? You know, simplifying it down. If I give you a parametric curve, are you comfortable about finding the values of t where it's horizontal derivatives, right? Where the tops of hills and bottoms of valleys are going. Are you happy about how you would find it for vertical tangent lines? Right. Make the top 0 gives you horizontal tangent lines. Making the bottom 0 gives you the vertical. Are we happy about special points? Right. That, you know, like you cancelled out a t minus 1 top and bottom, but that meant t equals 1 was some special about it, right? And if you were interested in finding it, you know, you just plug the t in. And lastly, if I give you a parametric curve, are you comfortable about how you would find the equation of its tangent line at any given point, which is the one we've just learned? A lot of that is very similar to what you would have done in Calc 1, isn't it? I mean, it's just adapted to a kind of new world. So for the last part of today, and we won't get these finished, and that's fine because I've pushed this homework on to next week because you've already got 3 sections, I believe. So wouldn't it be nice if we could also find the second derivative? And you notice I'm using that d squared y dx squared notation. That's just second derivative of a parametric curve. And its formula is nowhere near as elegant as the first one. So let me just write down above it the formula for finding the first derivative. If you want to find the second derivative, this intuitively is not so obvious. Would you agree that is not elegant? To find the second derivative, you differentiate this first derivative, right, with respect to t. That's what that means, right? Differentiate this guy with respect to t. It doesn't mean multiply. It's just got d by dt of this. So you differentiate this with respect to t, divided by the derivative of dx by dt. So let me try and sort of a pseudo prove this. It's not a formal proof, but it's the best I can do. Isn't the second derivative basically differentiating the first derivative with respect to x? That makes sense. Now, if you take this guy and you differentiate with respect to t, and then on the bottom you do dx by dt, I want you to think of differentials in the same way that you think of fractions. This guy in the bottom, if you bring him up top, is dt by dx. Do you see these guys cancelling out and shifting this over? Don't know how convincing that is, but that is kind of the weak, well, I don't know if you call it the reason, but that is why that second derivative is as weird looking as it is. Oh, by the way, see if you take this guy, top guy divided by bottom guy, top guy multiplied by reciprocal. Don't they cancel out? And guess what you get? Does dy by dx kind of make sense when you think of it in that term? So if you treat differentials as in the same way algebraically as you treat fractions, isn't there certain manipulations like the one we just did that work? Okay.
It's just
Here
like a
goes.
U sub.
Say again?
I said that's kind of like a U sub.
Yes. Like u is dy by dx kind of thing. Yeah. Okay. Let's do t cubed take away 1, and y is e to the t plus 2. Right? Want to make it nice and easy, not that they ever are easy. If you want to do the first derivative, you're going to get a fraction. Just that's what you get. That guy is e to the t, and this guy is 3t squared. So far, so good. Now, if you want to get the second derivative, this is our last question for today, you differentiate this guy with respect to t, and you divide it by dx by dt. So the derivative of dy by dx divided by the derivative of x with respect to t. Now, this fella has to be differentiated. If I rewrite this guy as 1/3 t to the -2 e to the t, can I do it as a product rule? If I leave it like this, won't it be a quotient rule? Would you agree that it's going to be ugly no matter which way I decide to do it? I just want to give you some choices. I'm going to keep it as that guy. So it's going to be f dash g take away f of g dashed over g squared. All divided by 3t squared. Differentiate the top, e to the t, leave the bottom alone, 3t squared, minus, leave the top alone, differentiate the bottom, and you get that, all over 3t squared squared, and that is just this piece. And that is divided by 3t squared. Can you see how ugly the algebra is getting? And we haven't even quite tidied it up. Right. So let's try tidying up a little bit. I'm going to pull out a t, e to the t, and a 3. And that's going to leave me with a t minus a 2. And that's going to be over 9t to the 4. And that's going to be divided by 3t squared. So we've got this ugly guy divided by this ugly guy. Algebraically, any suggestions what I could do next to try and make this a little bit nicer?
You divide by 3t.
Okay, so 3t cancelling out with this 3t. Okay, so I'll just leave the bottom as 3t squared for the time being. That cancels, that partially cancels, so it's going to get me 3 e to the t, t minus 3 e to the t, t minus 2. I'm still going to have three t cubed in the bottom, all over 3t squared. Okay, that helped. Where shall we go next? You know, you can't have a fraction with a fraction in it, right? That's just ain't going to happen, right? Not allowed. We're about 2 lines off the answer here.
To multiply by the reciprocal.
Okay, so essentially, I'm going to take this guy and I'm going to multiply by the reciprocal, which is that guy.
Okay.
Are we good? And now I can combine.
Yeah, no worries. Sounds good. All right.
And we're going to have 9t to the 5. Second derivatives are never pretty. Well, you should never say never in math, but pretty much never are pretty. Right? Are we comfortable with that process? Thankfully, I don't think you get many second derivatives to do, but you want to be aware that they're possible. First derivatives tell me pretty much everything I want to know about a parametric curve. Second derivatives really don't tell you that much. If you think back to Calc 1, they tell you if it's concave up and concave down. Not much else. So